Multimodal Large Language Models, or MLLMs, combine vision encoders and language decoders, but scaling them typically requires adding massive parameters or increasing sequential latency. Furthermore, the balance of computation between vision and language is traditionally locked at design time. Today, we are exploring ParVL, a parallel scaling framework that reuses existing backbone parameters across multiple parallel branches. This allows us to scale up computation dynamically and adjust the balance between vision and language processing, depending on the task at hand. The core problem with current MLLMs is their rigid, fixed compute allocation. Different tasks require different ratios of visual processing versus language reasoning. For example, document understanding demands heavy visual processing, while complex reasoning stresses the language decoder. Standard models cannot adjust this balance. Simply scaling up parameters increases memory costs, while sequential scaling increases latency. ParVL solves this by introducing parallel parameter reuse, allowing independent scaling of vision and language components. The key breakthrough of ParVL is its parallel scaling architecture that shares backbone weights while maintaining distinct processing streams. Instead of duplicating the entire model, ParVL instantiates multiple parallel branches using lightweight, branch-specific key-value prefixes in the attention layers. We denote the configuration as PV to PL, representing the number of vision and language branches. This design allows us to scale computation with less than a 4% increase in total parameters. To understand how ParVL keeps branches distinct without duplicating weights, we look at prefix-conditioned attention. Each branch maintains unique, learnable key and value prefixes prepended to the keys and values of the self-attention layers. After processing, a token-wise multi-layer perceptron aggregator fuses the parallel representations back together. This aggregation happens at modality-specific stages, ensuring that the shared language modeling head receives a single, cohesive representation. The main takeaway from ParVL's experimental evaluation is that the optimal compute allocation is highly task-dependent. By testing 9 different branch count configurations, the researchers proved that no single allocation rules them all. For instance, mathematical reasoning benchmarks perform best with language-heavy configurations, whereas document and OCR tasks benefit significantly from expanding the vision branches. ParVL allows us to tailor the compute budget to these specific task demands. ParVL consistently outperforms single-branch baselines across multiple scales, including 1, 2, and 8 billion parameter models. Because these branches run in parallel, the extra computation does not translate to a proportional increase in wall clock latency when hardware concurrency is available. To manage memory overhead, the authors also introduced a shared key-value cache optimization and explored a sparse routing mechanism that activates only the most relevant branch pair per sample. While ParVL presents a powerful new paradigm, it has a few limitations. Currently, the framework has only been evaluated during the supervised fine-tuning phase, using a 1/20th subsample of the InternVL SFT collection due to resource constraints. Future work is needed to explore how parallel scaling behaves during the pre-training phase and how it generalizes to other base model architectures and even larger scales. In conclusion, ParVL represents a major step forward in making multimodal LLMs more adaptable and efficient. By decoupling computational scaling from parameter growth, it allows developers to allocate hardware resources dynamically based on the complexity of the task. This pioneering study of two-dimensional vision-language compute allocation opens up exciting new avenues for designing highly specialized, cost-effective multimodal AI systems.